screen. Where'd the clicker go? Clicker?
Okay. Looks like we're ready to go. So our next speaker is Kyle Franson from UT Austin. And Kyle will be presenting on astrometric accelerations as dynamical beacons in a similar vein as Noah's talk, using this technique combined with direct imaging to search for planets and brown dwarfs around stars with dynamical acceleration. So take it away, Kyle.
Thank you. As Joshua mentioned, my name is Kyle Franson. I'm a fourth-year grad student at the University of Texas. I work with Brendan Bowler. I'm going to continue the theme of Noah's talk by talking about a program that we've been working on over the past couple of years to use astrometric accelerations as a target selection tool for direct imaging of planets and brown dwarfs. So in the past couple of decades, the community has done a really incredible job of assembling a population of about a couple dozen directly imaged resolved planet companions. In addition to these images, of course, being super exciting, these discoveries are now enabling real science to be done on these objects. One of those fundamental questions that we can ask about these objects is how they form, right? How does nature produce a 10 Jupiter mass object at a separation of 100 AU? Oh, it's giving me all my hidden slides, so you'll have to bear with me. Okay, so broadly speaking, there are three main formation channels that could be conceivably producing these objects. The first is core accretion, which is a classic bottom-up formation scenario, where dust in protoplanetary disks coagulates for planetesimals and eventually planets. Another possibility is disk instability. It's not playing my movie there, but the idea is that self-gravity in massive protoplanetary disks will drive the formation of spiral arms, which can then fragment under certain conditions to form planets. And the final possibility is that maybe some of these objects aren't really forming like planets at all, but are instead the lowest mass products of the star formation process. Oh no, it's not showing the plot. All my builds. Okay, we're gonna stick on this plot then. So if you'll note the red points, this is a plot showing. So one of the best tools that we have in our toolbox for constraining substellar formation and evolution are benchmark companions with dynamical masses and well-determined luminosities and ages. These systems are super valuable because one can compare the true dynamical masses of these objects with the predicted masses from substellar evolutionary models, as a way of both testing the model and its underlying assumptions about planet and brown dwarf formation, atmospheres, and pod properties. This plot here shows the handful of benchmark systems that have been measured thus far, at least the points in blue. And you can see that there's not a ton of these systems. That reflects the fact that these measurements are quite difficult to make. And most of these systems are confined to sort of the right half of the plot. So meaning that substellar formation and evolution is not as well empirically constrained at younger ages. And then finally, if you notice, most of these masses were measured relatively recently in the last few years. This is something that's really been kind of enabled just in the last few years. Okay, I'm gonna sort of go around here. Okay. So one can ask kind of what story do these current dynamical masses tell? And so the story so far has been that it depends, right? Some cases, the masses agree quite well with model predictions, but there's some intriguing cases where they disagree. Here's a few examples. The system on the left is a brown dwarf binary where the combined dynamical mass of the binary is 4.5 sigma lower than model predictions. The system on the upper right is 3.5 sigma, I think, lower. And the system and 4113C has a dynamical mass that's 6 sigma higher. And so all of these cases are underscoring that there's this pressing need to assemble more of these benchmark systems, more of these benchmark planets and brown dwarfs in order to really robustly, in order to investigate and resolve these discrepancies. And if I return to this plot, the idea is that we really want to canvas this diagram with a bunch of benchmark planets and brown dwarfs in order to better understand substellar formation and evolution. And of course, this is one lens to motivate the discovery of new planets and brown dwarfs, but there's a whole host of other reasons we want to as well, with the big one being having targets for characterization with, say, KPEC. Okay. The challenge, though, is that for the super Jupiters and brown dwarfs that we're currently capable of imaging, recent large unbiased surveys have found fairly low occurrence rates for these objects, with values of around 1 to 10%. It's probably not super surprising that the occurrence rates are at this level. We're really imaging the tip of the iceberg right now in terms of planet masses. If say we were imaging Saturns or Neptunes, the occurrence rate might be higher. But regardless, the takeaway here is that we really need a better approach to imaging new planet and brown dwarf companions. Oh my gosh. Okay. One way that we can overcome this low occurrence rate is by using astrometric proper motion information from Hipparcos and Gaia. So the idea is that wide orbiting planets and brown dwarfs will induce small proper motion differences over the 25 years between the two missions. And then we can use that as a way to efficiently search for planets and brown dwarfs that we can image by specifically looking at stars that exhibit these small astrometric accelerations, these small proper motion differences between those two missions. An advantage of this type of program is that because any stars in this type of survey would have significant astrometric accelerations that would enable the measurement of precise dynamical masses for any companions that are found, just like in the 5319 system. One sort of tricky thing is that it turns out that cross-calibrating these two data sets is non-trivial. But thankfully, Tim Brandt and Pierre Cravella all have both graciously done all the heavy lifting there and then released their results to the community. We happen to use Tim Brandt's HCCA, but both these catalogs are really fantastic resources. Okay, so diving into the HCCA. So there are thousands of, it's a super rich and powerful data set with thousands of accelerating stars. The plot on the left shows the log of the significance for the 115,000 accelerating stars in the HCCA. About 38,000, or about a third of them, are accelerating at a significance of 3 sigma or higher, which is fantastic. But of course, most of these systems are binaries. The plot on the right compares the magnitude of the acceleration between the DR2 and Gaia DR3, EDR3 versions of the HCCA in meters per second per year. And the takeaway here is that there are thousands of these stars that have these low magnitude accelerations that could conceivably be produced by planets. We just need a way of sifting through all the binaries. Okay, so the strategy that we use to select stars that have accelerations consistent with planets. So for a given astrometric acceleration, one can determine the companion masses that are consistent with it as a function of separation. And so for this plot on the right sort of shows what happens if you plot this up in mass separation space. You get these nice power laws that can display this degeneracy of the problem, where for a given astrometric acceleration, you don't know if it's caused by a close-in planet, a farther out brown dwarf, or an even farther out binary. But the problem here is that, so this plot here assumes that the acceleration is measured instantaneously, but of course that's not the case. And so when you incorporate the actual Hipparcos Gaia proper motion sampling and the orbital motion that companions crack out, you get this plot that has the power law at wide separation with all this rich structure as you march in closer. This companion is actually a benchmark companion with a dynamical mass. And so the star highlights the dynamical mass on both of those plots, and we see that it lines up better with a more sophisticated approach. Okay. Yeah, so the point here, though, is that with these plots in hand, one can envision really quickly identifying promising targets for an exoplanet imaging program. For example, the star in the upper left could be a brown dwarf, the star in the upper right could be a giant planet, and then we probably want to avoid the star in the bottom. This is binary. And so this is exactly what we've been doing on a large scale in our astrometric accelerations as dynamical beacons program, mining the tens of thousands of accelerating stars in the HCCA to efficiently search for and image new planet and brown dwarf companions. Now, just because a star has an acceleration that could be produced by a planet, that doesn't on its own rule out the possibility of a wider mass binary causing the acceleration. And so in order to mitigate this, we've been conducting a large observational binary vetting program with shallow, high resolution, and spectral imaging on facilities, including Keck. Okay. So here's a summary of the binary vetting that we've done so far. We have vetted over 500 accelerating systems, stars of visual binaries with high resolution and spectral imaging, finding about 35-ish% of those to be binaries. So this is great. We can sort of cast away those binaries before we do high contrast imaging sequences. And then on the remaining targets, we have hundreds of promising vetted accelerating systems, many of which are young, which would be great for looking for planets and brown dwarfs. Okay. We've recently started the deep imaging phase of our survey, obtaining deep high contrast imaging sequences for about a dozen stars with the vector vortex chronograph on Keck. We've confirmed the first discovery from the survey, which will be the focus of the rest of the talk. And then we have also identified a handful of candidate companions. Okay, so the confirmed companion is HIP 21152b. This is a imaged brown dwarf companion Hyades. It's an LT transition object. It was also independently found by two other groups, Bonavita et al. And Sahara et al. You may have caught their papers on archive recently. So we've been coordinating on a third independent discovery and in-depth analysis paper, bringing in all of the data on this object to do a comprehensive orbital atmospheric characterization. Okay, so here's what the mass prediction curve looks like for this target. I just showed this because I think it sort of illustrates why we're interested in this target in the first place. It sort of dips down into the substellar regime at around an arcsecond, so there's a ton of discovery space with this target. Oh, and then because it's a Hyades member too, that enables kind of precision model tests because of the precise age constraint from the Hyades. We have our team has low resolution spectra from Sphere and Taurus of this object, as well as photometry. The spectra and photometry are consistent with deep water absorption bands and maybe a hint of methane in the K-band. Companion situated at the elbow of the color magnitude diagram, which is consistent with a LT transition or early T spectral type inferred from the object spectra. And then we've also done a grid-based atmospheric model comparison, comparing it or finding the best fit model atmosphere to have an effective temperature of 1400 Kelvin and a sedimentation efficiency of 2, indicating the presence of clouds. Okay, and then sort of the big top line sort of science result of this, the dynamical mass of this object is around 25 Jupiter masses. And the interesting thing is that if we compare that with the model predictions, the model predicted masses are slightly higher in the sort of 40-ish Jupiter mass territory. And so this is another case where there's this modest discrepancy between the model predictions for this object and the true dynamical mass of it. Okay, so we can then return to this plot. I don't think this build is going to work right, but you just have to imagine that we're adding this object to the plot. Yeah, so just sort of looking forward, Hipparcos and Gaia accelerations are really effective tools right now for exploring kind of the middle region of this plot. So the wet brown dwarf and high mass planet territory. But in the future, with future Gaia data releases, future instrumentation like scales, along with especially the ELTs, we'll be able to really conduct really efficient and effective planet imaging campaigns, ultimately really robustly constraining in detail the formation and evolution of wide separation planets. Okay, so I'll splash up my summary slide and I'll take questions. Thank you.
Okay, I don't see any questions on the Slack channel associated with Kyle's talk. Do we have any questions in the room?
Yep, I have questions from Bruce and Adam again. Pointing at each other to go first.
So I had a question about the math. So we've now seen 2 talks where there was a difference in the dynamical mass and mass from other atmospheric parameters. Is there some, so either one could be wrong. Is there anything that would give rise to biases in dynamical masses with some incomplete information space?
Yeah, that's a great question. So the question is on what sort of things could possibly bias the dynamical masses that we obtain to possibly explain these model discrepancies. And I think this question gets at sort of there are multiple ways that you could have a discrepancy, right? So one is just the models are right. Our understanding of brown dwarf and planet physics is incomplete. Another possibility is that let's see. So for cases where the dynamical mass is lower, that means that the system is overluminous. So that could be an unresolved. That could always be an unresolved brown dwarf binary. Another possibility that's always present is if you have an additional companion in the system. And so like the classic system where like this is an example is HD 206-893b, where there was a dynamical mass that was, it's a really weird object just to begin with, but there was also a dynamical mass that was kind of different from expectations. And then that ultimately ended up being resolved with the discovery with gravity of an inner companion to the system.
Question is somewhat similar. You went by that slide quickly, but it did look like some of the Salmon and Marley models were overlapping with your dynamical phase space. Forward a couple more to the
Yeah.
Yeah, so the sort of state-of-the-art Salmon and Marley ones that think about cooling curves better. Which I think was done better on some of the binary ground dwarfs too. Yeah, so.
Yeah.
So it might be a clue as to which model, like, yeah, like you say, there's a lot of fiddle in the models. That just to make sure I understand the evolutionary chain, these model masses, because you're using spectrophotometry to get a luminosity, and then the luminosity of the age to get a mass.
Yep, yeah, so we're, at least for this object, I think, we obtained the luminosity using a bolometric correction, which is consistent with an SED-based luminosity for this object as well. And then we use that to get an inferred mass along with the age of this object.
Which wavelength are you bolometric correcting off of?
It's, oh gosh, I'll have to get back to you on that.
Yeah, so yeah, there are steps in addition to the interior cooling models, then you're sort of asserting your faith in the atmosphere models that give you the bolometric corrections, which
Yeah,
ways to mess up. So yeah, having the dynamic stuff is pretty very awesome. Can I ask you the same question about tying Subaru and?
I think we're done.
Okay.
yeah. I can get back to you on after the talks.
So I'd also say that there's a question online from Claire Max that perhaps Kyle could take a look at in the Slack channel and answer. Thank you.
Yeah, that's a lovely thing about Slack. We can just keep on asking questions.